Great. Okay. Well, welcome to the final lecture of our short course. I'm the only thing that's keeping you from our annual picnic, which is always, or at least in recent years, has always been traditionally hosted on the last lecture day of the short course. So it's ceremonial in many ways. I want to start, I have lots of slides, but I want to start this lecture just by kind of summarizing some concepts that I presented at the end of my very first lecture, because I think what's super important to understand is that there's actually a connection between the characteristic length scales and time scales of light interaction in cells and tissues, and the characteristics of the four most common diagnostic techniques in our field, as we've been learning over, especially in the last couple days. And hopefully, you'll be able to take away a better understanding of those interrelationships. So I'm going to try to make this interactive. I'm going to maybe make things a little uncomfortable on some level, because I'm going to ask you to try to recall certain things. But I think it's good. It'll be good, refresh. So we call this course a multi-scale biophotonics course, and it relates to these temporal and spatial scales. And really, when we're looking at imaging intrinsic contrast in tissues, there are really three processes that we need to think about. And that's really a single scattering, and then we know that in tissues, there's typically a directionality to that scattering. And in tissues, what did we learn about the angular directionality of single scattering events? When you have a scattering event, is the photon likely to scatter in all directions equally, or is there some sort of bias? It's anisotropic, right? And what are the typical, and what does the anisotropic mean? It has to do with the directionality of scattering. And in tissues, what is often the directionality of these scattering events? It's connected to the G value, but just using words, it tends to be forward. So you tend to, if you got a light beam interacting with a scatterer, you're more likely to scatter in the forward hemisphere than in the backward hemisphere, right? And so when we're thinking about the transition from a light field that is highly directional to a light field that's diffuse, where the photons have lost memory, in some sense, of their initial direction, that means you have to undergo multiple scattering events. And you can think of spatial and temporal scales where you've lost that information. And that's usually, you have a phone call, Bernard. Okay. And that's usually called isotropic scattering. And so there are length scales and temporal scales linked to what I would call isotropic scattering. It basically means how much multiple scattering, how many single scattering events do you need to have, or a photon path length that you need to have before the photon has lost all information or all memory of its directionality. And then, of course, the other very important process that we are concerned about is what? Other than scattering, what's the other thing that we are really interested in? Absorption, right? Okay, so we'll do absorption. Great. Okay, so I'm going to try to form a table here. I don't know how much real estate I have on this iPad, so we'll find out soon enough. And maybe I want to erase my little title to give me a little more space here, okay, to work. Okay. 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 So there were coefficients, right, associated with each of these um, processes. So I'm just going to call these attenuation coefficients just to use a neutral, right, a coefficient associated with each of these processes. And let's just focus in kind of the red to near infrared, just to kind of think about what we learned. So what are typical single scattering coefficients for tissue in the visible? I'm sorry, in the red to near infrared. Do you guys recall what values we tend to have in tissues?
Think about the numbers that Erin was saying when she talked about DCS. Said it multiple times.
0.01 was absorption.
Say that again.
0.01 was absorption and scattering was 1.
Scattering, what type of scattering was 1? Reduced scattering. So reduced scattering coefficient really relates more to isotropic scattering. It's, how many, it's a length scale associated with the loss of directionality. But just a single scattering, maybe think of it this way, maybe this can help you out. On average, how long can a photon travel within tissue before it encounters a scatterer? Do you guys have any recollection what that characteristic length scale is? And then the reciprocal of that length scale will be your single scattering coefficient. Single scattering 10 inverse millimeter, which would be about 100 micrometers, right? And that would be equivalent to about a G-value of 0.9. So there's actually a range because, some scatterers are very highly, there are a lot more of them, and there's the single scattering coefficient is high, but they have a high G. But I'm going to just, for argument's sake, I'm going to take a value on the higher end. And I'm going to take 100 per millimeter. But you can go down to about 10 per millimeter. That's also firstly acceptable. But I just want to highlight kind of contrast between these spatial scales. And then isotropic scattering, I think we already got an answer, right? What was the mu s prime? Someone... 1 per millimeter, right? So if you do mu s prime, this is about 1 per millimeter. Okay? And then absorption, anybody? 0.01, that's a good value. Okay, terrific. Okay, so I think it's really important to kind of have, a certain intuitive sense. I mean, I'll defer to give Anna some credit. It's 10 to 100. Okay, so there's a range there. And of course, mu s prime also, there's a variability. In skin, it tends to be much higher. It could be 2, 3, depending on where you are in the spectrum. The dermis is very highly scattering. So this is just kind of, gets us in the right order of magnitude. So then these all link to a spatial scale, right? So the reciprocal of these relate to a length scale. Okay? And so if you have a mu s in the range of 10 to 100, what does that mean in terms of this, what we call the single scattering length, L sub s? Okay, so if we've got attenuation, mu s of 10 to 100 per millimeter, what does that mean in terms of length scale? Single scattering lengths. Say that again? Yeah, that's right. Or 10 to 100 microns, right? So you've got 10 to 100 micrometers. Okay. And then in terms of isotropic scattering, I like to call this, I can call this L star, although L star has a couple different definitions, as Hector reminded us. In some of the literature, it's 1 over mu s prime. In other references, it's 1 over mu s prime plus mu a. But let's just be in this spectral regime where mu a is much lower than mu s. And so L star would just be 1 millimeter, right? Because the reciprocal of the mu s prime is 1 millimeter. And then you can define a characteristic length scale for absorption. And what would that spatial scale be? If we've got a mu a of 0.01 per millimeter, what is the characteristic length scale on average a photon has to travel before it's going to be absorbed? So the reciprocal of 0.01, 1 over 0.01 is equal to 100. So you see right away, you got to travel 100 millimeters, 10 centimeters, right? It's like 4 inches. I mean, it's actually a fairly large distance, but that's where multiple scattering really helps us, right? You don't need to have a source to texture separation of 4 inches or 25 millimeters to just get a loss of half your photons. It's the multiple scattering that makes the photon trajectories very tortuous, so that even if the source to texture separations are small, the actual path length of the photon is much larger. Okay, so the other thing we maybe think about much less is that these length scales, yeah, I'm running out of real estate here, also imply time scales. Okay, and so we know, from our undergraduate physics that, time is just a distance divided by a velocity. Okay, right? And so our distance is basically our length scale, whatever it is. It's going to be L sub something. We have different subscripts that we're using. And the velocity in this case is what?
Refractive index is also.
Yeah, but what the speed of what are we considering the speed of? Speed of light in the tissue, right? So in this case, it's going to be the speed of light divided by the refractive index, n, okay? And what n do we usually use for tissue? 1.4, something like that. Just to make the numbers easy, I'm just going to make this 1.5 because we know the speed of light is 3 times 10 to the 8th meters per second. And if you divide this by 1.5, it becomes 2. It just becomes a nice, easy number, right? So I'm going to do 1.5. It's really 2.2 almost, but just for convenience, I'm just going to divide by 1.5, and you have whatever else. Okay. So what we're going to do is that we're going to basically take each of these length scales and divide the length scale in meters divided by 2 times 10 to the 8th meters per second. Or you can even think about this as 2 times 10 to the 11th millimeters per second, since we tend to put our length scales in millimeters. Okay, so let me also write that here. So this is 0.01 to 0.1 millimeters. Okay? So can anyone do that computation quickly in their head? What is the time scale now for single scattering in your tissue? I'm going to call that T tau scat. What is that time? The time, that's literally the time the photon is able to travel in the tissue on average before it's scattered. So if you put that in a calculator, and I'm using the mu-s of 100 per millimeter, or a mean free path or scattering length of 10 micrometers or 0.01 millimeters, you'll get the value of 50 femtoseconds. Okay. And that, kind of in some sense relates to the timescales that you would probably want to use or, within reason for the time resolved frequency, time resolved reflectance, getting much smaller than that doesn't really give you much advantage, So your length scale for isotropic scattering is about 100 times longer than that. So that means the time should be about 100 times longer, right? So that's for isotropic scattering. I'll call that tau star. This is going to be 5 picoseconds. Okay? And so that, that's the amount of light, amount of time the photon can propagate, or the photon field can propagates before it loses its memory of direction. It becomes an isotropic field. And then for absorption, you're again 100 times longer, right? So now you have what's called in the field the absorption relaxation time. So what time is that? 100 times longer than the isotropic scattering. So that is 500 picoseconds or half a nanosecond. Okay? So this gives you a sense of how long the photon field propagates before it starts to get extinguished due to absorption. Okay? And this also implies things about frequency as well. Okay? So any questions about this? So hopefully this is kind of making some connections or sense relative to what we found before. So again, now I want to talk about, so we want to be in domains in each of our measurement techniques where we're sensitive to scattering and absorption separately, right? And so each of these techniques leverage the fact that we try to sample the light field either in space or in time in domains where we're sensitive to attenuation or modification based on scattering versus absorption. So you can think about this, obviously, in the spatial domain, we tend to have detectors close to the light source. Typically, since you lose directionality on the order of a millimeter, for spatially resolved, we tend to see that we want to have one detector within a few millimeters within the source, ideally, and one much further away from the source so that we can sample absorption. Okay? And there's an analog to that in the spatial frequency domain. So I'm running out of, how do I scroll here, Bernardino? Or maybe I can't scroll. When I use my finger, it just draws. Let's see. What I can always just start a new page. This one? Oh, okay. Ooh, everything. I think that's created a new one. Okay. Okay. Hopefully that's okay. Do you guys get everything down? Okay, great. So you can imagine that in the spatial domain, say in spatially resolved diffuse reflectance, you want to kind of probe the field, the light field, on spatial scales less than or on the order of L star and much larger than L star, because at short source detector separation, you're probably going to be more sensitive to scattering. Whereas at larger source detector separations, you're going to be sensitive. In reality, you're going to be sensitive to both, but I'm just going to say you need to sample that light field at those spatial scales to have any hope to look at absorption. Okay? Okay. So this also has an analog, or I always like to think in terms of, I think of the consternation of many, but I always like to think of this in a dimensionless way. So I often think about this in terms of you need rho over L star. This is dimensionless. You want to look at this on less than or on the order of 1, and you need rho over L star here, much larger than 1. Okay. So let's think about this in the spatial frequency domain. Okay. So in the spatial frequency domain, you have a period of light, a spatial period of light that you use, and that's called the spatial frequency. And I always think about it in terms of radians. So the radians in a full spatial frequency is 2 pi. So in spatial frequency domain, I think of, well, you can use spatial frequencies. I'm going to call this 2 pi fx. You can look, and this has the units of inverse length. You can think about frequencies that are much larger than the characteristic frequency of transport. And so the spatial frequency of transport would be the transport mean free, 1 over the transport mean free path. Or, so these would be high frequencies where you're probing the tissue on spatial scales that are, or on spatial scales that are smaller than the time it takes for light to lose its memory of its directionality. Or you can do it on spatial scales less than that. Okay? So in this first domain, again, so these are high spatial frequencies relative to L star. So what do you think that's going to be sensitive to? If we probe on spatial frequencies much higher than the characteristic frequency given by isotropic scattering and also absorption, what do you think we're going to be probing mostly? Yeah, you're going to be probing scattering. Yeah, and in some cases, single scattering if you get high enough. And conversely, in this case, absorption, right? Okay, and again, I'll write this in dimensionless terms. Okay. Okay. And then we can start to think about this also in the temporal domains. Maybe I should pause here. I want to make sure I'm not losing people. Does this make sense? This basic framework? Okay. So in terms of time domain reflectance, I'll call this time domain reflectance spectroscopy. We need to think about times related to scattering and absorption. So if you're probing your domain on times less than or comparable to your scattering time, which we call T star, you're going to be sensitive to scattering, right? And if you're going to be probing on times larger or comparable to your absorption relaxation time, you're going to be sensitive to absorption. Okay? Right? Okay. So again, so this implies we saw what were the scattering relaxation times? They're on the order of picoseconds, right? So this is going to be on the order of picoseconds. It's as short as 5 picoseconds, but in reality, it'll go out. Whereas here, it's around 500 picoseconds, or about half a nanosecond. And of course, this is the mean time, right? So to accumulate that information, you often have to probe longer, but this is 500 picoseconds. And then there's going to be an analogy in the temporal frequency domain. So in temporal frequency domain, often called FDPM, frequency domain photon migration, this whole field emerged well before spatial frequency domain. And so that's what in the field, we just call frequency domain, but it's temporal frequency domain. We have a similar thing going on. Now here, we're modulating in time, okay? So, and you can think about this, again, I'm going to think in terms of radians. So you have 2 pi times your modulation frequency, which I'm going to use lowercase omega. Okay, so this is a temporal modulation frequency. And you can think in terms of much larger than the absorption relaxation time and much smaller than the absorption relaxation time. I think that's what I should have done in time domain, looking at it. I should really just think of this in terms of, let me see if I can do this. Here we go. Okay, I'll just think about this. If you're much smaller than the absorption relaxation time, you're going to be sensitive to scattering. So you're going to be, basically less than 500 picoseconds. This is more. Similarly here, you can be at spatial frequencies much slower than, hold on, I have a problem here, don't I? I do have a problem here. Units are not making sense, right? Because omega is in reciprocal, so this should be to the -1 power. Okay. Okay. And if you go through the math, you find that if you want to be, so this is going to be more sensitive to scattering. This is going to be more sensitive to absorption. And this means that you need frequencies greater than about 200 megahertz if you go through the math. And that's why, as we learned in our previous lecture, we're in the hundreds of megahertz because we need to probe. We actually ideally need to acquire data on frequencies slower than it takes the light to get extinguished and faster to probe scattering. Okay, so we're gonna look at these maybe more in more detail and more, with nice fancy plots and figures. So hopefully you'll get this. But what I really wanted to really delve into is that the fact that we're probing on these space and timescales are not by accident. You can almost derive them directly from just the fundamental optical properties and the understanding of speed of light in tissue. Okay, that the actual place in measurement space where you're making these measurements to get sensitivity of absorption and scattering can be derived, what we did this, in 10, 20 minutes, right? Okay. Any question? I mean, I dumped a lot of information in a very short period of time, but does this kind of make sense? Or are people kind of lost? Which is fine. If we're lost, then let's talk about it, because I think this is kind of central to some of the takeaways in this course. Okay, so let's switch the slides. We're going to be coming back to this again. Darren, do you have any input, or you're good?
Yeah, we'll often use modulated frequencies. Around 100 megahertz.
Sure. Maybe, can you use microphone? Sure. Yeah.
When we practically take FDPM measurements,
Yeah.
We used to do a lot of sweeps, but
Sure.
these days we do single frequencies.
Yeah.
And we'll use a frequency around 100, 125 megahertz. And
Right.
that seems to work pretty well for us,
Right.
both in modeling and experimentally for separating absorption from scattering.
Okay.
And it just, your cutoffs here at 200 megahertz, I mean, I don't know, there might be some more nuance there. It's not a strict cutoff.
No.
Like it is a little bit more with spatially resolved, right? As you really get close, you really become very insensitive to absorption.
Yeah.
But at 100 megahertz, you're still going to be sensitive to both absorption and scattering.
Yeah. Yeah.
Some
So
degree.
yeah. I'm not saying that you're only sensitive to scattering
Right.
absorption. Often in the domains where you're sensitive to absorption, you're also sensitive to scattering.
Yeah.
So I'm just trying to look at extremes and kind of give them an intuition that we're looking at hundreds of megahertz, not tens of megahertz,
Right.
or not 1 gigahertz, right? This is the domain you need to be in. So these are not strict cutoffs, but I wanted to kind of connect where we're measuring in measurement space. They are linked to these intrinsic spatial and time scales. And that's why I have these, I don't always say, well, I got a little sloppy. That's why I always put this, these squigglies get me out of a lot. It's less than or similar to, you're in that domain. These are orders of magnitude rather than factors of 2 and 3. But that's a really important point. And the other thing we'll see shortly is that the sensitivity characteristics of amplitude versus phase is a little different. And if you're capturing both, that also gives you some additional information that may help separability. Yeah. And so we'll get into these details, but I think conceptually, I want you to understand that. Are there any other questions? Okay, so let me see if I can manage yes, stop mirroring. Okay. What do I switch back to, Bernard, if I want to get back to the laptop?
Stop it.
Oh, just stop. Okay, thank you. Okay. Okay. So, okay. I guess I should have talked about my teaching objectives, but I think you're getting a sense of them already. So, connecting spatial and temporal scales to our measurement domains. I want to delve a little bit into standard diffusion approximation. Darren talked about these already a little bit, but we'll apply the standard diffusion approximation to model reflectance signals in both spatial and temporal domains. I'll delve a little deeper into time-resolved and temporal frequency domain reflectance, talk about sensitivity to optical properties and the pros and cons between spatial and temporal domain methods, okay? And so we talked about spatially resolved reflectance. I just told you a little bit about them. The take-home messages are that your optical path length, the optical path length of the photons, when they emerge from the tissue, increases with source detector separation, right? And that for source detector separations less than or on the order of L star, we saw yesterday in the lab that if you increase μs, you're going to increase your reflectance, right? Because you're really probing light that's been minimally scattered. And if you increase the local density of scatterers right below the source, you're going to get more light out very close to the source. And you're not really sensitive to absorption because the path lengths are too short. But if you're on source detector separations much longer than that, the light has accumulated more path length. That gives you sensitivity to absorption. And of course, absorption attenuates the light. But interestingly, if you increase scattering at these larger source detector separations, your reflectance also drops because the scattering serves to increase the optical path length of the photons before they're detected. And so the impact of scattering has an intrinsically different impact whether you're short or far away from the source. And short means on the order of L star. Long means much larger than L star, okay? Again, there's the squiggly. Usually it's around 2 or 3 L star, okay, where that cutoff happens. And we saw that, right? We saw the spatially resolved reflectance curves cross over, right? When we looked at different optical properties. And that tended to happen around 2 to 3 L star, okay? So hopefully people are comfortable with that. And then, of course, we can look at the Fourier domain of this, and that's spatial frequency domain reflectance. And again, there's here I put spatial frequency in terms of wave number k, but basically, as your spatial frequency increases, you are collecting light with reduced optical path length. And that's because if you kind of think of this in terms of 2 bright lines that you're illuminating with, if the bright lines are far apart, they have to scatter quite a bit in order for you to lose that intensity modulation in space. And so it's retained in larger depth. And so the light that comes back that still retains that can actually travel a fair amount. But if those lines are really short, close together, you know, the light just travels a little bit before scattering is going to just wash that out. And so your high K values or high spatial frequencies are really preferentially sensitive to light that has undergone a much smaller optical path length. And that also has to do with depth of probing, right? You're going to probe much more superficially at high spatial frequencies. So it also means that when you're at low spatial frequencies, relative to L star, you're going to be sensitive to absorption, and you're going to be also sensitive to scattering, because again, scattering is going to change the optical path length, and it's going to it both changes. And it's actually a little different than spatially resolved. You actually get an increase in reflectance with increase of scattering, even at low frequencies. At high frequencies, we lose sensitivity to mu A, because again, path lengths are short, and if you increase scattering, you're going to increase your spatially resolved reflectance, even at high frequencies, just like at short source detector separations here. Okay, and so we're going to build this up again for our temporal domain. Okay, and we'll shortly come up with the rules here. Okay. Okay, so let's talk about quickly. We saw this already, going from radiative transport to the diffusion approximation. Just a reminder, we're using a very simplistic and maybe oversimplistic conceptual mathematical model for the radiance and the phase function, basically treating it as a linear sum of an isotropic term, something that's uniform in all directions, plus something that has a bias, a cosine theta term, both in terms of the radiance, the angular distribution of the light field in the tissue, and the single scattering phase function. Okay, and then if you do lots of fun math, shove these into the radiative transport equation, and do a lot of manipulation, you get this standard diffusion or diffusion approximation. And when you go when you're in the time domain, you have this option of whether you want to keep the second derivative term or not. Okay, if you keep the second derivative term, you're in the P1 approximation. If you throw it away, you're in the standard diffusion approximation, but you have the deficiency that you don't have finite time of arrival. If you get rid of the second derivative term, at any time larger than 0, you have light everywhere. It's infinite velocity of propagation, okay? So that creates a problem, obviously. And then the other thing is that we lose information about single scattering, right, when we're diffuse. And so we don't see mu s anywhere here. You only see mu s and mu s prime. And that means that we lose any sensitivity to the angular distribution of scattering. We lose sensitivity to G. All pairs of mu s and G that give you the same mu s prime value will give you the same prediction. Okay? Okay, so this is a review. We've looked at this before. We're not going to go through the details. Spatially resolved reflectance, we see, it adopts a much simpler formulation. Your spatial decay goes with this mu effective term, and we talked about mu effective quite a bit. And you can treat your source as a diffuse source. So the light transport of a collimated source decays with mu tr, which is just the sum of mu a plus mu s prime reciprocal. Okay, so if you remember from your differential equations, that when you solve a differential equation, you first solve what's called the homogeneous equation without the source term. And that will give you, in this second order differential equation, spatial scales given by 1 over mu effective. You actually have a positive exponential and a negative exponential. Usually in a semi-infinite medium, only the negative exponential survives. But if you have a slab, you actually keep both of them. Okay? And then you also have a spatial scale linked to the spatial decay of your inhomogeneous term. So these solutions tend to have exponentials that are related both to mu effective, right? The square root of 3 mu A times mu TR, and then mu TR by itself, okay? And we looked at solutions for those. I think Darren, you presented some of these in your lecture. And so again, photons detected at small distances travel short path lengths, insensitive to mu A. Reflectance is most sensitive to scattering at small rho. And then at large, you're sensitive to absorption. And this gives you a sense for the correspondence between Monte Carlo and SDA. You see that for very high scattering, it's doing pretty well. It starts to break down on the order of L star here. As you go moderate to high or absorption, it actually doesn't do well anywhere, which is unfortunate, but that's the reality. That's why we have Monte Carlo and lookup tables and all the wonderful things. Okay. Again, this is review. Just want to remind you, and if you have any questions, this is the good time to ask. Okay, so let's look at time domain. Again, we tend to look at standard diffusion approximation. You can show this in different ways. The interesting thing about time domain is that there's a simple solution for an isotropic point source in infinite media. And I want to look at the formulation of that equation because it gives you the insight into the physics. And this is also the first way that people in our field, now over 35 years ago, try to analyze that temporal point spread function. The first thing is that if we look at source detector separations let's see. This is going to, there we go. If we look at source detector separations much larger than L star, the reflectance has a very simple expression, relatively simple expression. And here I'm looking at the time derivative of that expression. And what's interesting is that the time derivative has a very simple form that can be leveraged to essentially to isolate mu sub A. And if you look at that expression in two limits, for large times, these two terms go away, and all you're left is that the derivative of the natural log of the reflectance is linearly proportional to mu sub A. So it tells you if you plot reflectance on a log plot, the slope at large times is directly proportional to mu A. Okay, and you saw that in the curves that Darren showed you, right? That as the absorption went up, that reflectance drops off faster with time. The other thing that was really interesting is that if you take a derivative and you set this time derivative to 0, right? Remember in your first calculus class, when you set a time derivative to 0, you identify a minimum or maximum. So here you find out that actually if you look at time derivative equals 0, it turns out you can isolate mu s prime. So at the point in the time domain curve where the reflectance reaches its maximum, you can actually solve for mu s prime. So the time at which that expression reaches its maximum, and you've already determined mu a through this curve looking at large times, you can actually solve identically for mu s prime. So there's actually an analytic solution for getting mu a and mu s prime. One by looking at the slope of the curve at long times, and one at looking at the time at which you measure your maximum reflectance. And this was super convenient, albeit it has its limitations, but it was a really neat way to separate mu a and mu s prime in the olden days. Okay, so this is kind of cool, and so what I'm going to do here is show. Oh, I'm sorry, a question. Yeah.
Questions in the previous slide.
Yes.
So those relations, let's say at the end of the slide, are directly derived from the fluence expression on top, or do you
Yeah,
first
well,
need
yeah.
to?
So,
Mhm.
of course, when you are measuring things in a semi-infinite medium, you have all of these boundary effects and things like that.
Yeah.
So it doesn't give you absolute values, but it gives you some scale. Yeah, these expressions are derived from the reflectance, which is related to this.
Okay.
Okay.
Mhm.
You look at this paper is
Mhm.
where all of this is derived.
Yeah.
Okay.
And then, in order to be able to apply the limit for large T and
Mhm.
the relation for mu prime,
Yeah.
I guess in the log scale we need the decay to be linear.
It is linear.
Okay.
Yeah.
Could it happen that it's not linear? Let's say short source detector separations, strong absorption.
When it's strong absorption, well, you have to be a large source detector separations here. Okay, that is
Yeah,
an
that's the condition. Yeah, you're right.
intrinsic
Mhm.
limitation of this.
Yeah. Mhm.
And so if you're in that domain, I don't think there's anything else here. This is just attenuation, right? So remember, when you're going in time,
Mhm.
that's directly related to path length.
Yeah.
So all the photons that you are collecting at a given time have all traveled the same path length.
Yeah.
And so that rate at which you're extinguishing light is directly proportional to mu A. And I think that's independent of any approximation.
Mhm.
Okay? Because you know that all of those photons have done that fixed path length. I think the error, if there is an error, comes in the mu S prime.
Mhm.
Yeah. Yeah. Good question. Other questions? Okay. So I'm not going to look at the fidelity of the inverse model, but I want to just show you, inverse models in recovering optical properties. So I just want to show you the correspondence between SDA and Monte Carlo. So again, you see one thing that regardless of whether you're in high scattering domain or low scattering domain, is that SDA will not predict the time of arrival very well. And I actually can't remember whether this is SDA or P1, but essentially we saw in P1 that there is a second derivative term in time. So there is actually a finite time of flight, but the velocity is actually wrong. So standard diffusion approximation will, or P1 will always predict earlier arrivals than what happens in reality. But even though it's wrong for the highly scattering, it actually predicts the time at which you reach the maximum pretty well. And there was the value in that old, expression. And it's pretty much nailing the decay. So it's doing pretty well. And even at 10, it's not too bad. So you can see the value of those simple analytic expressions. And 3 and 1, yeah, it gets worse. There's no question. And then here is at spatial scales, detector locations much closer. And here you see even worse agreement. Even after, first, you don't get the peak at all because your prediction at early times is bad. And even the decay, you have to be at much longer times before you get the decay, but the decay is actually not too bad. Okay. Okay. I have more of these curves. I don't want to belabor them. I think you can look at them. But I think, here's the same curves at different source detector separations. And then in highly absorbing medium, like this. One thing I want to just, this is kind of unrealistic from an experimental point of view here. Look, I'm plotting things over 16 decades. Obviously, there's no instrument in the world can measure 16 decades. I think the group in Italy has made some really strong advances, right? They changed their amplification at various times, right? I think they can get up to like 4 or 5 orders of magnitude, I think, in their time resolved reflectance, which is quite a feat. But anyways, this gives you a sense of your time decay. Okay. So what we learned from this in terms of temporally resolved reflectance is that, again, optical path length increases with time. In fact, there's a direct relationship between time and the optical path length. And that if you're probing the system at large source detector separations relative to L star, you know that for times on the order of the time it takes for a photon to directly go from source to receiver without any scattering, you're going to have higher reflectance with higher mu sub s. And at time scales where you allow the photons to be extinguished due to absorption, your reflectance goes down with increased mu a, and the slope actually gives you the information for mu a directly if you're on a natural log, a log curve. And so we're going to try to develop these relationships for the temporal frequency domain. And this slide was to cue me to try to do something on the board to try to build some intuition on temporal frequency domain reflectance. I'll just say kind of biographically and personally, I was recruited here to BLI by our former director, Bruce Tromberg, to work on what he called photon density waves. And it's still very challenging for me to get a good conceptual understanding of this. For me, there's still something mystical about photon density waves. And I'll try to do my best to get a real concept, to try to build up some sort of conceptual understanding, even though I think my own conceptual understanding is incomplete and imperfect. Bernard, can you give me the keys to the kingdom of your iPad since it has timed out? Thank you. Okay. So, so the first thing that it took me a long time to really understand is conceptually, what are the spatial and temporal scales associated with this modulation? Remember, we're doing light as a carrier of this intensity modulated wave. And I think for the longest time, I couldn't really understand that. Maybe it's because I wasn't trained as an electrical engineer. Maybe it's because I'm stupid, but it took me a long time to get my head wrapped around this. So the first thing I want to just think about is, light has an intrinsic frequency, right? So if we look at the frequency of light, okay? Okay, thank you for letting me know. Why is that? Okay, let's see. I have to do, oops, sorry. Great, thank you, Bernard.
Sure.
If we just think about the frequency of light, it's the velocity of light over the wavelength, right? Okay. And, again, I'm going to just simplify. In tissue, I'm going to approximate the velocity of light by 2 times 10 to the 8th, meters per second. And our wavelength, let's just keep things simple. Just say we're using 1 micrometer, right? So 1 times 10 to the minus 6th meters, right? So that frequency, if you do the math, it's 2 times 10 to the 14th, or 200 terahertz, okay? So this is the fundamental rate oscillation frequency of the electromagnetic wave, okay? Okay, now, as we learned in our previous lecture, practically, we make measurements using modulation frequencies on the order of 100 megahertz, okay? So the frequency, I'm going to call this the frequency of the photon density wave. Let's call it 100 megahertz, okay? So remember, what we're doing in frequency domain is that we have a wave that we're modulating in time, right? We have to have a DC offset, right? So there's like an average intensity that these photodiodes are giving out. Let's just call this, I'm going to do that here. And what we're doing, and so this is intensity, right? And we're modulating this in time, right? So, I'll do my best to draw a sine wave, something like that, right? And if we're at 100 megahertz, this time is 10 nanoseconds, right? Okay. But we have to bear in mind, in this, we have the carrier, right? And the light is oscillating, orders of magnitude faster, and this is the envelope on which the carrier is floating, right? And this is happening in time, and this is then propagated in tissue. So the first thing Bruce would always tell, this is the wavelength of the photon density wave. I said, what is this wavelength? It just drove me batty. Okay, so the first thing, so how do we get a wavelength, right? We say, well, we want to know what is the physical distance that this amplitude modulated wave travels in a given oscillation, right? And so that, again, so the lambda of the photon density wave, and so we're assuming there's no scattering here, okay? Just imagine this photon density wave traveling in a clear tissue without scattering. The effective wavelength of this is going to be the velocity of light in the tissue divided by the frequency of the photon density wave, okay? And if we do that, we get 2 times 10 to the 8th meters per second divided by the frequency of our photon density wave, 100 megahertz, that's 10 to the 8th, right? Hertz. And so this gives you a wavelength of 2 meters, okay? So this, if we're propagating through a tissue without scattering, the physical distance of one oscillation of an intensity modulated wave at 100 megahertz is 2 meters. But in reality, the light is multiply scattered. So it can't propagate 2 meters because it's constantly getting multiply scattered. In reality, the wavelength of the photon density wave in tissue is probably a 100th of this, okay? And it's probably on the order. So in tissue, so let me call this I'm going to call it in air, but of course I used a velocity of light in tissue, but this is, maybe I say a clear tissue. In a turbid tissue, because you have multiple scattering, it's much smaller than this. It's on the order of, say, 2 centimeters, okay? I'm not giving you a rigorous derivation of this, but multiple scattering has that impact. Okay. So the other thing I want to talk about is phase, right? Darren talked about that we're measuring amplitude and phase. And I want to give people some sort of intuition about phase. But maybe I should pause here and to see if there's any questions about this. And Darren, if you want to editorialize, I welcome it because I think there are many different perspectives on how we conceptualize this. But Najib has a question.
So I didn't get what's the frequency of PW?
Yeah, so this is called photon density wave. The frequency of the photon density wave is what in the lab, the rate at which they intensity modulate the source, meaning how quickly do they blink the photodiode, the laser diodes on and off. And Darren showed a whole bunch of data where they do these frequency sweeps, typically from 0 out to maybe as high as 500 megahertz. But and you mentioned that sometimes you get really valuable data at around 100 megahertz. You can still separate absorption and scattering. So that's the actual rate at which they're blinking the light sources on and off.
And the smaller, like the higher frequency sine wave is the light?
Yeah, this is the light. That's interesting. Of course, I didn't put in as many oscillations as is needed because you're different by what, 6 orders of magnitude. So in one of these cycles, you have literally 1 million oscillations of the electromagnetic field.
Thank you.
Yeah. Oh, okay. And I think Anna has a question.
Oh, no, I was gonna turn this thing back on, sorry.
Oh, okay, sorry.
I can do this for a second.
Sure.
I was just gonna ask
Thank you.
how do you get conceptually I can't wrap my head around how like a turbid tissue.
Sorry, say that again?
Conceptually, I'm having a hard time wrapping my head around how you would conserve some sense of wavelength, but like decreased within a turbid media.
Right. So think about it this way. So this 2 meters, just pretend I'm a photon density wave and there's no scatterer. I will propagate a certain distance in a given amount of time. And that's the 2 meters. But if all of you, yeah, but if all of you prevent me from going in a straight line, I'm going to be going left, right, and center. And in the same time, during the time it takes for that photon density wave or the light source to blink on and off, I can't travel 2 meters. I can only travel a couple centimeters. I think you told the story of you meeting Bruce for this first time at SPIE. You have all of these people blocking him. There's no way he can, right? And so, you can imagine, basically, people may have seen molecular dynamics simulations. All these atoms are bumping into their neighbors, right? And so the light is bumping into all of these scatterers. In that time, it can't travel 2 meters. It can only travel a few centimeters. Does that help a little bit?
Yeah.
Yeah.
You conserve that. You conserve a sense of how your intensity is being modulated because
Right.
the photons are being.
But the physical
interacted.
distance that wave can propagate is much reduced because it's been bounced around. Is there another analogy, maybe, Darren? Or you're good? You're good with that analogy? Yeah. Okay.
So if we think
Brian.
about the total distance, maybe like a photon has traveled, will they be the same for clear and turbid tissue?
Well, that's a complicated question to answer. I think thing is that the optical phase relationships are all screwed up, right? Because even the photons in the photon density wave are all traveling in different directions. And so I don't quite know how to answer that question. Darren, do you have any?
No, I don't know either. It's a great point.
Yeah.
It's not one thing, it's many photons.
It's many photons that are captured within this envelope, right? It's not one photon, right? So I think you have a ensemble average of path lengths within that wave. Other questions? Okay. Don't worry, this is not the last of it. I'll give you many more opportunities to get confused. So, okay. So let's talk about phase. I said I was going to talk about phase. So let me deliver on that promise. So phase, whoops, sorry. So phase, remember phase is that, is you're subdividing the wavelength into radians or degrees, right? So, and I want to know that if the photon density wave has traveled a certain distance, what phase has accumulated in that travel? So if I just look at phase, I would just say, well, you have 2 pi radians, right, in one cycle. So you have to take 2 pi, and then we got to consider some sort of path length that you travel, and you divide it by the wavelength of the photon density wave. Okay? And if we consider the path length to be a direct time of flight, again, no scattering, then let me just consider this path length as the source detector separation. Imagine that you have a source and a detector and you're injecting light through a medium that has no scattering. you're going to encounter a certain phase from that, and that would be just 2 pi rho, which is the source detector separation. And again, the wavelength of the photon density wave is just the the velocity over the frequency of the photon density wave. Okay? Right? Velocity divided by frequency is wavelength, right? So if you do that, let's just say that we have a source detector separation of 1 centimeter. Okay, just again, to keep the numbers easy. So we're going to do 2 pi, and 1 centimeter in meters is 10 to the minus 2. Okay, and then velocity, again, we're keeping it simple. I'm going to say it's 2 times 10 to the 8th meters per second. So hold on, this is rho. Sorry, this is rho. This is velocity, meters per second. And our frequency, we're going to do 100 megahertz, right? So that's 10 to the 8th, right? Well, what does that equal to? If you do the numbers, it's 3 times 10 to the minus 2 radians, which is 1.7 degrees. No scattering, okay? Direct time of flight, you will accumulate a very small phase delay, okay? But what in reality happens is you undergo multiple scattering, the path length effectively is longer, and therefore you're going to accumulate much more phase than this, right? Because the photons are not traveling ballistically. And so in some sense, the phase tells you something about the path length of the photons and traveling source and detector. The other thing I want to really emphasize here is that the phase is linearly proportional to the frequency of the photon density wave. So if you double the frequency, you're going to double the phase delay. So basically, if you see a linear relationship between phase and modulation frequency, it means that there's intrinsically nothing changing with respect to the optical path length of the photons from source to receiver. Okay? It's like a linear propagation, not a linear propagation, but a wave that has the same effective velocity in the medium. Nothing is changing. And that's important, and we'll get to that later. So it's really important to recognize that if you change scattering, that's going to change this path length, and then you're going to change phase. And so that's why phase is really sensitive to scattering. And then we already talked about, I think, what's really important in this area is the absorption relaxation time, which is, a distance divided by the velocity. In this case, the distance is 1 over mu sub a over the velocity. And this is about 100 millimeters in tissue, 2 times 10 to the 11th. And so that ends up equaling 0.5 nanoseconds. And if you convert that to a frequency, that's, the equivalent frequency is 200 megahertz. Okay? Okay. Okay, so now let me confuse you more with slides. Okay, any questions? Yeah, Darren, please.
Just a practical note about calibration and phase.
Yes, please.
When we measure tissue with FTPM, we might get the tissue inducing several degrees, maybe 10 degrees of phase shift, depending on the modulation frequency and the scattering.
Yeah.
The instrument itself induces plenty of
Yeah, it does.
of phase, right? Sometimes tens, hundreds.
Hundreds, right?
Yes.
Optical fibers and all this, yes.
Exactly. You're
Yeah.
accumulating phase just from that photon density wave traveling through the fibers. So you have to remove that, and you do a calibration, but it's a little bit different than the calibration I showed.
Mhm.
In phase world, you want to subtract off the
yeah.
phase that's accumulated
That's right. It's
in
a
the
subtraction,
instruments.
not a division.
Exactly.
Yes.
Amplitude, you still do a division, but for phase, you do a subtraction. Same steps in many ways, right? You have a phantom with known optical properties. You use a forward model so that you know this phantom should supply X degrees of phase. And then you force your measurement to give you that degree of phase by subtracting off what the instrument's contributing.
Thank you, Darren. That's really an important thing. And I think you have that paper from 2000, Tuan Pham, RSI. They talk about, I think, in that how they take away the instrument response and how you have to deal with the amplitude and phase differently. Yeah, Bernard, please.
Are there any questions? Are there any issues with phase wrapping? Or is it the phase so small that they pass the instrument response?
Right. No, we have plenty of issues with phase. Yeah. Okay. So, for example, when you do a frequency sweep, measuring many modulation frequencies, the phase will typically grow with modulation frequency, as Vasan just mentioned. Right. When you do a frequency sweep, you'll have higher phase shift as modulation
Oh,
frequency goes
sorry.
higher. But remember, phase keeps wrapping around 0 to 360 or 0 to 2 pi. And the instrument will measure some phase shift. And what we actually measure typically is phase, not in an absolute sense, but compared to some reference channel. Like in the instrument I showed you earlier, we have an analog to digital converter where one of the channels is just measuring the electrical signal we generate. We pick off a little bit of it and send it to one channel. And the other channel is being converted into an optical signal that goes through the tissue, back to the detector, and into the second channel. And we're measuring the phase difference between the two channels. And so wherever you happen to be in that 0 to 360, you may have this phase jump, and you have to do phase unwrapping. And you can actually get confused, especially in the boundaries at which, for lack of a better term, wrap you're in.
Yeah.
Right? You can kind of get the same answer and be in, 1 degree or whatever it is, 299 degrees. Yeah. It's caused trouble. Thank you.
Other questions? Okay. I'm
Are you done?
done with the iPad, actually. That's the end of it. Yes. Thank you. Do you want take this? Oh. Do you want me to unplug? I need to unplug it.
Go ahead.
Okay. Thank you, Bernard. Okay, so I'm going to take you through some of the messy math. But again, this is more, hopefully, give you some conceptualization of how we approach this. So again, this is the time-dependent P1 approximation. And what we do to solve this is that, well, we know that we're putting in light that is okay, great. Oscillating with time. And we want to recover amplitude and phase. So that means there's a real and an imaginary component to that wave. And so we just assume time harmonic oscillator, essentially, as we assume that we're putting in a source that is a harmonic oscillator. And therefore, we expect that our fluence rate is going to behave as a harmonic oscillator with a modulation frequency omega. Okay. And what we do is that we basically put these two terms in to this equation, and you get and you transform this P1 approximation that has dependent variables of location and time to an equation that has dependent variables of location and temporal frequency. Okay. And what happens is that the equation looks exactly the same, pretty much, as your P1 approximation, but this attenuation coefficient now has real and complex contributions, so that you get attenuation of that wave, the amplitude, and you get a phase delay associated with that. And the degree of that attenuation is linked to the absorption relaxation time. And this tau star is is essentially the scattering relaxation time, but actually it's a transport relaxation time. That does include mu A. I can give you a reference if you guys are really interested in the math, but I won't trouble you with that right now because I think what's more important is developing an intuition for how these things work. So you can solve this. Phi can be subdivided. I think you already mentioned this, Darren. The measured fluence rate as a function of location and time can be subdivided into two terms. One is the real component of the attenuation, how that thing is damped in amplitude, and how you get phase accumulation. And so you have a attenuation wave vector we call K real and K imaginary, and you have beautiful math here. To derive those, again, if you're mathematically inclined, I can give you the references. The math is actually really cool, but I think for the purposes here. And then you can simplify this further in the standard diffusion approximation. There are a few things that happen that you can get rid of some more complicated terms. So let's look at some plots, okay? So what I'm plotting here is a medium with L star equals 1 millimeter and a mu s prime over mu a of 100. In this specific case, your absorption relaxation time is about 340 megahertz. And what I'm plotting here, the solid lines are the attenuation of the amplitude of that wave as a function of modulation frequency. And I've put an unrealistic range of modulation frequency. Typically everyone is operating at 500 megahertz and less. Often you're only around 300 megahertz. But what you see is that the damping of the amplitude of the wave doesn't change very much with modulation frequency. And if anything, there is some variation in the damping that's more prominent for high scattering media as opposed to highly absorbing media, okay? So you're really not sensitive that much to changes in the amplitude with spatial frequencies in more highly absorbing media. You're more sensitive to it at highly scattering media.
Temporal frequency, right?
Temporal frequency, yes. Yes. But generally, if you have any sensitivity, it's going to be at frequencies, slower than the absorption relaxation time, okay? In terms of phase, one thing you see is that at very low modulation frequencies, your phase basically accumulates linearly with modulation frequency. And then once you get past the absorption relaxation time, you start to see a bend over. You start to see dispersion. We'll talk about why that's the case in just a moment. And for very high modulation frequencies, this actually, the K imaginary scales as the square root of the modulation frequency. And the reason this is the case is that when you start modulating on time scales faster than it takes absorption to occur, you basically you're no longer, you actually peel off or you no longer measure the photons that are being extinguished due to absorption. And so there's a subpopulation of photons that are no longer being detected. And therefore, you're actually filtering out, let's see, am I saying this correctly? You're filtering out a subpopulation of photons, and you're actually enriching the photons that have traveled shorter path lengths, okay? Because if you're including all the photons, even the long path length photons, you'll have more of a linear relationship. But as you start to kind of filter out those photons that get attenuated, you actually are enriching the ballistically traveled photons. And we'll see that in phase. I'd like to show some plots. This is all simulated. This is using actually, I generated the results using the GUI, using scaled Monte Carlo, but then I changed things a little bit, as you'll see. I'm plotting these things in a non-traditional way relative to the literature. So here I'm keeping source detector separation fixed relative to L star. Okay, L star again is the transport mean free path, 1 over mu A and mu S prime. And I'm keeping mu A fixed, okay? And all I'm doing is I'm changing mu S, which really means that in physical space, each of these curves are generated at a different source detector separation. Because if I'm keeping mu A fixed and I'm changing mu S prime or mu A, then the physical transport mean free path is actually changing quite a bit by a factor of 10 going over this range. And what I did is that all I did is I plotted the amplitude normalized to the maximum amplitude. So I just want you to get a sense of how the amplitude decays as a function of modulation frequency. I did a more modest range of modulation frequency, only out to 1 gigahertz. And then this again is the absorption relaxation time. What you see again is that you get relatively modest decays in the amplitude so long as you're below the absorption relaxation time. And that at around the absorption relaxation time, you almost kind of roughly what I would call you reach a maximum in the second derivative. You start to accelerate in the attenuation, amplitude attenuation of the wave at larger frequencies. I'm plotting the phase in a very non-traditional way here. What I'm plotting the phase, I compute the phase and I divide it by the phase that you would get if there was no scattering in the medium. Okay? So it's the phase you measure divided by the ballistic phase. And that basically gives you path length of the photons relative to the path length if you had a direct path from source to receiver. So what this tells you is that for mu S prime over mu A of 100 at very low modulation frequency, the path length that the photon density takes is about 6 times longer than a direct time of flight from source to receiver. And this is where I talked about you enrich the ballistically traveled photons as you increase in modulation frequency. You disallow, as you increase in modulation frequency, you disallow a subpopulation of photons that would normally get absorbed at long times. And as you increase the modulation frequency, you're rejecting more and more of them, and you're enriching the ballistic photons. And that's why this phase, normalized phase, of course, the physical phase increases, okay? But if you look at the normalized phase relative to direct time of flight, you're basically enriching the portions of the photon density wave that has undergone less absorption and therefore a more direct path. And I find this kind of, at least for me, helps me understand the physics a little bit more. But I don't think I've ever seen a plot like this in the literature. But I think to help the concept, it's helpful. Okay. Oh, okay. So now these are the really confusing slides. Okay. Sensitivities. We want to understand how are we sensitive to changes in scattering and absorption. Okay, so here I'm plotting sensitivity, the derivative of the amplitude that you're measuring in the photon sensitive wave over mu A, okay, your absorption sensitivity. Full disclosure, this is the negative of that value because that would be always negative, right? You increase mu A, the amplitude has to go down. And because there's such a large dynamic range, I had to do this on a log plot. So this is super confusing. So this is the highest change in the amplitude due to absorption and least change here. And so you tend to be very sensitive to changes in absorption in media that are highly scattering. So this is why breast tissue is like the best tissue for frequency photon migration. You typically have very low blood volume fraction. You have great sensitivity to absorption. You try to do this in muscle, it's really hard. You really lose sensitivity to absorption because the baseline mu(S)prime or mu(A) in something like muscle is much higher.
Try to do it in the SWIR, right, which we're thinking about.
Why don't we put on the microphone if we can?
Yeah.
Where's the microphone? Yeah, I want to capture that comment. Please, Darren.
Hard in muscle, but also in the SWIR, where your mu(S)prime over mu(A) is going to be lower,
Yeah,
right? You simply have less sensitivity.
that's right. I did some calculations quickly with Vrinda. Yeah, there's even before you get to the water peak, mu(S)prime mu(A) is around 20, 10 to 20, right? And so it's tough.
And that affects absorption.
Let's get the microphone. Thank you, Darren. What affects
I
absorption?
was confused on, you were talking about the SWIR region
Right. So
and how it makes it less sensitive.
Right. So
at those
this is
wavelengths.
your intrinsic sensitivity of the amplitude of your photon density wave to absorption. These are modeling 4 different types of tissue where the baseline optical properties in the top case is where you have a highly scattering tissue, where mu(S)prime is about 100 times larger than absorption. In the SWIR, because of absorptions of lipid and water, you tend to have baseline optical properties that are much more highly absorbing. You're around between 10 and 20, I think, in much of the SWIR region. And your sensitivity to change the absorption is almost 2 to 3 orders of magnitude less. So measurement in absorption amplitude is going to be really difficult for you to determine changes in absorption precisely. Okay, does that answer your question?
Yes.
Yeah, okay, great, thank you.
I think these plots are as confusing as useful, but I mean, yeah, they are really, they
Yeah,
tell you a lot of things, right? Just one question about these 2 last plots.
yeah, I haven't talked about the right one yet, but we'll
Okay, yeah,
get
but
to it.
yeah, so maybe they are like normalized to something or not. I don't think perhaps the left, one to
The left one is not normalized.
okay, and the
The right one is not normalized either.
okay. Mhm.
Yeah, okay. Okay, the right one is a challenging one. And so, and I made a disclaimer at the beginning of this lecture that I don't fully understand this either. I mean, it's really, it's a tough topic, at least for me. So this is the sensitivity of the phase to absorption. And so the first thing is that you reduce in phase as you increase in in temporal modulation frequency. That makes sense, right? Because we talked about in the previous plot how your phase, not your physical phase, but the normalized phase actually goes down with modulation frequency. You're not collecting a subpopulation of photons that will get absorbed because you've turned the light on and off before those photons could get absorbed. So as a result, what we're doing here is that we're increasing absorption, right? That, in some sense, will force you to ignore more of those photons, right? And so that's why your sensitivity phase goes, I mean, it's a negative value. Now, the shape of these are interesting. This kind of tells you, at least for the highly scattering media, you see that actually you get most of this drop early, and then they start to moderate. In some cases, they hit a minimum, which I don't quite, I think this is an accurate result, but I haven't quite wrapped around the explanation for it. But here, as you increase your modulation frequency, you're really, you're rejecting more and more of those photons that would have undergone absorption, but that you're not detecting because you're modulating fast. And once you get beyond that, you've gotten rid of most of them and your sensitivity kind of plateaus. Okay. Now, why you should reach a minimum and for it to come back, I had an explanation for it yesterday, but I can't remember it right now. But I think the basic feature that I want to emphasize is that you actually have a good variation in sensitivity to absorption with phase at low frequencies, and that's perhaps very useful. Yes, Darren.
Don't quite understand the relationship with mu s prime over mu a. Why are
Yes.
you more sensitive in phase to mu a as you go to lower ratios?
Yeah, that's a good comment.
That actually seems quite useful practically.
Yeah. And in some ways it's a good, I'm trying to actually see the consistency here, which I'm not seeing right away. Here you change by a factor of 2 and you have this drop from a little over 6 to a little under 5. Here you change by a factor of 2, you're seeing this drop from about 3.5 to 2.5. I guess fractionally this is a bigger drop than here. So I think that's where I think those two plots are consistent with each other, but why that's the case, I don't have an immediate answer. Yeah, but that's a good observation. Yeah, Hector.
Yeah, in the plot to the left,
Yes.
why did you choose to plot the negative rate
Oh,
of
because I needed to use a log scale because
Yeah.
of the dynamic range. And of course, you can't do the log of a negative number. So that's
Yeah.
why I just made all the numbers positive and then took the log.
Okay.
Because otherwise, if I did it on a linear scale, you'll just see this and maybe this curve, but you wouldn't be able to see those other curves.
Okay.
Yeah.
Yeah, I'm a bit confused. Like maybe you can apply the same to the.
Well, I don't need a
Right.
log here, right? It's
You don't need a log,
log.
but yeah.
Yeah, but I could do, but basically your phase is going down as you increase mu a.
Okay.
So I think the negative is helpful there.
Mhm.
Here, it's just your attenuation is highest here.
Yeah, it's a matter of representation. Okay.
No, it's, I agree. It takes some time to wrap around this. And then now we have the scattering sensitivities. And again, you're going to have more sensitivity to scattering for more highly scattering media because your path length is longer. And you're going to have a more intrinsic sensitivity to that. And then with phase, this predicts you tend to be more sensitive to changes in phase at more highly absorbing media than highly scattering media. And I think it's because your phase is so small at the highly absorbing media. So remember, these are fractional changes, right? It's a derivative, right? So if you increase scattering just a little bit in a sample that's highly absorbing, it's going to really contribute to your phase. Whereas if you have a very highly scattering media to begin with, and you change it by the same linear increment, you're not going to have as much an increase in phase. So that's good. You're going to have, if you're really trying to target scattering changes in a more highly absorbing tissue, and you have enough baseline precision in phase, then you're in good shape. But none of this considers what is the intrinsic precision of your device, right? And I imagine that in a highly absorbing media, you may be running against some intrinsic limits in terms of what is the minimum phase you can actually measure with precision. So this gives you the fundamental physics, but ignores the realistic limitations of your instrumentation, which can be very different in a highly absorbing medium versus a scattering medium. So these are plots, they're information rich. I admit, sometimes difficult to interpret, but I think can be very useful to think about if you're trying to design an instrument or trying to figure out where in measurement space you want to measure. Okay. So with that, we can return to our master slide. And basically, we essentially have understood that as you increase modulation frequency, you tend to be collecting photons with slightly smaller path length. And so that means that your amplitude tends to go down as you increase either absorption or scattering. And your phase tends to go up either when you reduce absorption, because you allow for more scattering, or you increase scattering. Okay, and so those are good rules of thumb. And so I think we're at the end. So these are our teaching objectives. I hope I didn't confuse you so much, and we'll take questions, and I'll let Darren answer all of them. Thank you so much. Questions? I think they need a break. We do have a picnic. That's technically already started. Okay, let's adjourn. Thank you, guys.